Hey guys, welcome to Fundamentals of Chemistry, Section 2, Classification of Matter. So we're starting to get into some real chemistry here, y'all. So right off the bat, we're just going to go straight into states of matter. We know that there are accepted 4 states of matter: solid, liquid, gas, and plasma. We don't use plasma very much, plus it irritates me because plasma isn't technically matter because it isn't made up of atoms anymore because you have completely plasmalized atoms. Anyways, I can go on a tangent, but just understand that we don't use that one. So we have solid, liquids, and gases. This is essentially what they would look like if you were to look at their particles. In this beaker, solids would maintain a shape, liquids would kind of take up the bottom of the beaker, and then gases, of course, expand and fill the whole beaker. So organization-wise, gases have no real pattern. They fill their entire area with random arrangement. They have pretty wide spaces between them, and they move in all directions very quickly. Liquids, they do have a random arrangement with no major pattern, but they only generally fill the bottom of the container they're in due to gravity, of course. If we were on a different planet, they would fill the container very differently. So we are just talking about Earth. Their particles are generally close together, and they move and slide past one another very easily. Solids, however, are in a regular, usually grid-like pattern, although not always a perfect grid. All the particles are going to be close together, they're touching each other, and they are still moving. They still have some kinetic energy to them, but it is not very extreme. So basically, that's what you're going to see is that the particles are going to be really close to each other. So going from a solid to a liquid is basically adding heat. Going from a liquid to a gas would be adding heat. And then if you were going the other way, going from gas to liquid, it would be subtracting heat. Going from liquid to solid would be subtracting heat, okay? And there's words to describe those changes, and we'll kind of come back to those in later units and talk about them. But for right now, I just wanted you to kind of picture what the particles would look like. So this is the overall classification of matter, and some of these words and things may look familiar to some of you because certain classes, certain class periods, we did get to go through that chart. Other ones we didn't. So I'll tell you at the end of the video, for those classes that did get to go through the chart, you'll stop at a certain point in the video. Those who didn't, you'll go for an extra minute or two to fill out the chart, so that way you'll all have it together by next class. So this is the basic idea here. We start with the idea of matter being everything that isn't energy, essentially. Pure substances are anything where they are pure, all the particles are the same. So on this side of the chart, all the particles are the same particles. Excuse my handwriting with an S. Same particles. Elements and compounds, if all the particles are identical, then it is an element. If you do have some particles bonded to others that aren't the same, it's a compound. We'll go into that in a minute. Mixtures are when you have different particles, and they are not bonded, okay? And we'll talk about that again in a minute. So pure substances contain all of the same types of atoms. They could be elements or they could be compounds, just depending on what they're made of. So in this one, this will be an example of an element because all of the particles are identical to one another. Down here, while all the particles are the same, so like this particle is the same as that particle, so they are the same substance, but you will see that the black circle and the white circle are two different elements, essentially, at that point. So compounds are made up of different elements, but if all of the particles, if all of the pieces of the compound are the same, then it is still pure, essentially, right? Because you still have a glass of water. That's pure water if it is pure distilled water, but it is a compound. It is made up of hydrogen and oxygen. So you have two different elements that still combine to make up that compound. The term molecule is not exactly interchangeable with the term compound, so I don't want you to get too hung up on it, but we will go into a little bit more detail later in our bonding chapters when we talk about the difference between molecules and compounds and things, but essentially, anytime two or more atoms are bonded together, it is a molecule. If those atoms happen to be different, then it is a compound, okay? So looking over here, this is a compound. The middle one, well, the first one is a compound and a molecule because molecules are anything that's two or more atoms bonded together. These happen to be different in the first box, so that also makes it a compound. The middle box is a molecule, yes, but it's an elemental molecule because each of the atoms, each of the smallest pieces are identical. In the bottom, we're back to a compound, also a molecule. So all of these are molecules because they have two or more things bonded together. Only two of them are compounds because they have different elements bonded together. here's another chart just kind of splitting that idea of elements and compounds apart again. We have some examples here, so make sure you fill out this chart. I'm going to scoot past it because I've already talked about everything on the slide, but please pause it, write down the things from this slide, and then you can move forward. However, what happens if you put more than one pure substance together, but you don't bond them? Well, if you listened earlier, you know the answer. You get a mixture. Two or more things that are together but not chemically bonded are a mixture. There's two types, heterogeneous mixtures and homogeneous mixtures. Heterogeneous means different. So what that means is that you can easily see the different parts of a heterogeneous mixture, like this one, okay? This looks like it's in the liquid state. This looks like it's in the solid state. So you would see, and so looking for those states of matter does help. I mean, this may be even gas. I don't know. But being able to tell the difference would help you identify that, one substance has separated itself from the other substances, or perhaps two substances down there at the bottom have separated themselves from the others. So if you can see the parts separately, it's a heterogeneous mixture. In this one, it's all kind of thrown together. Sure, this is substance X, maybe that's substance Y, whatever, but there's different substances in there, but they are all kind of mixed together evenly. So if I were to zoom out and look at this, I wouldn't be able to tell the parts apart. Again, heterogeneous mixtures are easily separated because you can easily see the parts from them. A couple examples, things like fruit salad, Italian dressing, sand and water, oil and water. Those are all good examples of heterogeneous mixtures because you can see the components separate. Homogeneous mixtures, it's difficult to see the components separate. Salt water is a great example. Once you dissolve it, that is not a chemical reaction. Water dissolving just means you are taking the salt, salt dissolving, you're taking the salt, you're spreading it out around in the water. It doesn't mean it's reacting with the water. So dissolving is not a chemical reaction. So anything that dissolves in water and quote-unquote disappears is going to be an example of a homogeneous mixture. Food coloring, Kool-Aid, salt water, sugar water, any of those things that you can dissolve into water and they essentially, quote-unquote, disappear and you can't see them separately, sure, when I put red food coloring in water, it turns red, so I know the food coloring's there, but I couldn't look at it and individually point out where the red pigment molecules are and where the water molecules are. It would be very difficult to see them separately, and thus, it would be a little bit more difficult to separate them. But because they're not bonded, any mixture is not bonded. So the substances that mix together don't bond with each other. So because of that fact, you can separate them. And here's the methods on how you can do that. So right off the bat, you're probably going to need to pause the slide because I'm not going to talk for an extremely long amount of time. So you'll probably want to pause it, write down the stuff, and then, or listen and then pause it, okay? But these are the physical separation techniques. We have filtration, we have magnetism, evaporation, and distillation. Those are the four different separation techniques. You probably can logically figure out how these work. Filtration, while you're filtering something. You can separate solids from liquids using things like filter paper. You could separate solids of different sizes using screens or sort of wire mesh, if you will, to keep back the larger particles. So I've given you some examples over there, and it does tell you the instruments you would need. You could use beaker, funnel, and filter paper is what you saw in the apparatus for filtration. So that's kind of the solid from a liquid situation. That's probably the most common you're going to do this year. We will have a lot of times where we pour two liquids together, they create a solid within them, and you need to filter it out to get the mass of it. So that's going to be the one that you'll practice a lot. Magnetism, well, you use a magnet, and it only works if it's magnetic. And that's it, okay? Usually it's a magnetic substance from another non-magnetic substance. Evaporation is usually done when it's in water, and water is the substance that is evaporated. In that case, the solid that you want to get is dissolved. And when we say something is dissolved in another thing or dissolved in water, it is aqueous or aqueous, okay? So an aqueous solution means that something is dissolved in water. It is, and water like aqua, if you can remember it that way, aqueous, aqua. And so generally that's going to be a solid that's dissolved in the liquid, so like salt water. If I have salt water, I can't see the salt, but I know it's there, And if I boil the water and the water disappears, the salt will be left over. Maybe you've done that before. Maybe by accident. Maybe you left it on the stove or something like that. So you'll get a chance to see that next week as well, so you can see kind of how that evaporation process works. You obviously need a heat source and usually a beaker or some sort of funnel, okay? Distillation is the one that we don't really do in this class. If you move up into IB and AP, you will do more distillation, but in general and honors chemistry, we really don't do distillation because it does require some pretty extensive apparatus that are difficult to come by. Generally, that's when we want to separate and isolate different liquids, okay? And you'll see on the next slide kind of how that works. All right, pause, write down everything from the slide, and then go to the next one. Okay, so I didn't put a magnet on here because hopefully you've seen one, but these are some of the general ideas for how these processes work, okay? In the first one, you see that you have an evaporation system, so this is evaporation. And we have an evaporating dish there that also could be a beaker, okay? We have a heat source of a Bunsen burner that also could be a hot plate, okay? So really you just are required to have some sort of heat source and some sort of container to hold the substance that you're evaporating. Water would leave the substance. Anything left behind is what you're going to get, okay? The middle one is filtration. Filtration. In this case, we have the filter paper would be located inside the funnel. The funnel is suspended over the beaker. Sometimes, depending on the size of the funnel, the size of the beaker, you really could just rest it in the beaker. But one of the problems that comes with that is that if the cone is really deep and the liquid gets to be really high, it's going to stop filtering. So that's why we suspend it usually above it, unless you have a very shallow cone. This is a distillation process, or excuse me, a distillation. That is not a distillation apparatus. And so this is basically the solution you're starting with. You boil it, and it moves up through here. And then it goes through the fractioning column, meaning that anything that is really heavy is going to stay behind, and then whatever is kind of lighter is going to boil all the way to the top, and then head down here, condense, and go in there. Okay. Usually, no, it didn't have to be water. I don't know why I was going to say it had to be water, but the fractioning column keeps behind any of the heavy molecules, and they fall back down, and the lighter stuff heads out that way. Okay, so this is the review. As a reminder, you have pure substances and mixtures. Those are the big categories of matter. Physical processes can separate mixtures back into pure substances. Those are our four separation techniques, okay? So that's distillation, evaporation, magnetism, and filtration, okay? Compounds, sure, can be turned back into elements, but that's going to be some sort of chemical reaction, and we are not quite at that part of the year. But rest assured, we will be, okay? Go ahead and write this down. For those of you that already did the classification of matter chart, where we talked about what they're made of and we drew some little particle diagrams, you can pause the video now and be done. For those classes that didn't quite get to that, switch to the next slide. I'm going to run through that and copy that down, and we'll move on from that. Okay, so I wanted to do particle diagrams for these because I know there was some in there in the video, but I wanted you to get to see kind of how I drew them in class, okay? So for elements are made up of atoms, okay? And they are all made up of the same type. Okay, so all of the atoms would need to be the same type for it to be considered an element. Are they chemically bonded? Sometimes yes, sometimes no. So you could say both, okay? For elements, sometimes they're going to be single, sometimes they're going to be together or partnered. So boop. On the single side, we could just have some of the, assume that these are circles. Clearly I'm struggling, but assume they're circles. So it could just be single particles. And so some examples, we could have, I'll just give you one. Carbon, or anything else that's on the periodic table of elements. Sometimes, however, we'll have particles where there's two identical particles that are stuck together, okay? Let's put it up there. Okay? That each individual atom is still the same. Okay, so that is still considered an element. One element that does this is oxygen. Is a good example. Okay, so let me change my color real quick before I move to the next one. All right, compounds are also made up of atoms. but they are different. Okay, they're made up of different elements. So that means that they are multiple atoms that are from different types of substances that are, yes, chemically bonded together. Okay, a good example. Let's do this one where one of them's shaded and one of them's not. So if you see a particle like that, that good example of that would be carbon monoxide. Okay, most of you have heard of carbon dioxide. Carbon monoxide is just CO. So looking at the formula, it's pretty straightforward. You can see carbon, you can see oxygen. Well, if you can't see that yet, by the time you use your periodic table, you'll start to get that. Okay, but you can see that there's two different substances there. They are bonded together into this molecule, so that is a compound. The other one is, of course, our upside down Mickey Mouse. And if you don't recognize that from biology, that is water. Okay, water. And the formula for water, of course, is H2O. So what stands out there, of course, is that we have hydrogen and oxygen, two different substances. They are connected in the diagram, so that means they are bonded together. Okay, moving over to the other side. Moving over to the other side, we have heterogeneous mixtures. They are made up of a mixture of pure substances. Okay, and if you recall, the pure substances are elements and compounds. Okay, so they're made up of a mixture of pure substances. Are they chemically bonded? No. No, they are not, okay? They are not chemically bonded. In a heterogeneous mixture, we've already seen a picture of that, but what it might look like, of course, would be two substances that are not the same, and they are separated in the container. So you can actually physically see the separation. So they are not... Nope, I don't want to say not mixed. Not dissolved. Not dissolved, or they won't mix. So great examples of that, of course, would be oil and water, or sand and water, or anything like that would also be good. And then the last one, homogeneous mixtures. Homogeneous mixtures are, again... Sorry, I hadn't changed my color. Are again a mixture of pure substances. Okay, they are not chemically bonded. Make that super clear. But if you were to look into a container or something, you would have the different particles would be suspended with between one another. So you would still see, you would not be able to see really the difference between them. It would be difficult to identify, oh, that's where the carbon monoxide is, that's where the water is, etc. So these are evenly mixed. Okay, you can still separate any sort of mixture. They're still separatable. It just may be a little bit more difficult. You may have to do a more obvious, or excuse me, a less obvious process. Great example would be salt water. Okay. All right. So go ahead and stop it here. Make sure you've written all this down, and I will see you guys next class.